Okay, welcome to the fourth class meeting of EECE574, the graduate level probability and random processes. First, please check the new electronic attendance system for your attendance. And if you want to correct it, please provide relevant documents so that I can update the roll book. There goes announcements. Homework 2 will be assigned today or tomorrow, and due will be next Tuesday so that you can efficiently utilize your long weekend this time. Handout for chapter 2 is updated because I had some typos, so please especially replace the first few pages from before section 2.0. And as you know, passwords are all lowercase letters, characters for numbers related to the PDF files, ONE, TWO, such as thing you type in and file will open. Recorded class meetings are uploaded to the YouTube channel, and you can place clickable timestamps. So in your comment area, place like 1 colon, 2, 5 colon, 3:30s, which means the 1 hour, some minutes, some seconds. Then you put the topic of what is explained, and that will greatly help people who will view the videos later. Messages from instructor. Since you are all graduate students, I really want to emphasize the importance of simplification and visualization. So try to exercise these two methods to efficiently solve or create new problems so that you can be a good researcher in the future. Here goes the overview of this course. We are still reviewing the undergraduate material related to probability and random variables, and probably up to 2 random variables. And then we will move to the topic of random vector and a sequence of random variables. And then we will study general concepts related to random processes and also some related important topics on random processes. I found no special corrections or clarifications on the last class meeting. And here goes the review. So last time we started to study the concept of random variable. In our undergraduate course of random variables and processes, random variables was roughly defined as an outcome of a random experiment, but not a specific realization or instantiation, but the variable with uncertainty in itself. However, that concept does not match well with our mathematical concepts already learned. So when I was an undergraduate student, that rough definition was very strange and even misled me that a probability theory is something totally different from other area of mathematics. However, in this graduate course or some undergraduate courses, you've just started with a probability space as you did for the probability part, chapter 1. So here is a random experiment mathematically modeled by a probability space consisting of the sample space, the event space, and the probability measure P. And here goes an outcome, lowercase s, it denotes. And then here is a mapping rule that maps individual outcome to a real number. Okay. Then we can say the output of the second box is just simply capital X of S. And this follows the standard method of describing a system or a cascaded system using a block diagram, right? So here, X is nothing but a mapping rule that maps an element in the sample space to a number in the real line. Got it? So given an outcome, which could be a numeric value already, or which could be totally abstract, like red, green, blue, or banana, apple, strawberry, something like that. For any outcome, this mapping rule maps it to a real number. In that sense, this mapping rule is called a real random variable. Got it? Now, how can we match this new mathematical model with what we learned in undergraduate program? So we put these two boxes together into a bigger box, and then we say that this source that generates a random number is equivalent to a serially cascaded random experiment followed by a mapping rule that generates a random number. Got it? So here goes one of the most fundamental questions. What is a random variable? And then you can simply say that it's a function or it's a mapping rule satisfies such and such property, something like that. By the way, there are one more important exception in this description, because sometimes we really want to change this codomain of the mapping rule as the extended real line, which contains all the finite real numbers and also plus or positive infinity and negative infinity. As I emphasized last time, as an engineering school student or a scientist, the physical or engineering meaning of infinity is what? A number or numeric value is sufficiently large. In order to mathematically, rigorously handle that kind of daily life concept, we use the limit. Of course, the limit itself has a meaning. However, in many, many cases, the limit operation should be interpreted by an engineer that for sufficiently large something. Okay, so never forget that. So infinity means infinity mathematically, but for engineers, for sufficiently large. So this F dot, S dot, L dot is very often used in engineering school courses. You can write it. Your advisor may quickly understand, instantly understand what you mean for sufficiently large. Anyway, so there are two types of random variables. Its range is those who have the range, the real number, and the others who have the range, the extended real line. Got it? Of course, the second group is very small compared to the first one. It is very important in many cases, because I once myself had a big confusion on this difference and made some mistake even in my graduate course. And another one is this classification. So you may say that, okay, here is the set of all real random variables. And you may say that, okay, the codomain is R, and here codomain is R bar. And also you can divide the same set of all real random variables into like discrete, continuous, mixed, singular, something like that. Okay? We are mostly interested in discrete, continuous, and mixed cases. And how can we divide that? As you remember, we use the notion of cumulative distribution function. before we talk about CDF, let me review one of the other important concepts. So since we can view this serially connected two blocks into a single one, we can imagine an induced probability measure. Fortunately, to be short, let me just present the result. We can take the real number as our sample space if our random variable resides in this set. Okay, so we take simply the real set as the sample space, and then we take the Borel sigma field or Borel sigma algebra for our sample space. It's always enough. Okay, mathematicians have proved it. And then here goes something strange called the induced probability measure. This induced probability measure has its input from this Borel sigma field. And each element of this Borel sigma algebra is called a Borel set. For example, this open interval is a Borel set. This open interval is also a Borel set. Of course, this, that are all Borel sets. Okay? Because one of the reasons is that the Borel set is constructed in a way that you consider all possible open intervals, and then you construct sigma algebras that contain those open sets. And you intersect sigma algebras to get the Borel sigma algebra. So Borel sigma algebra is the kind of minimum, the smallest sigma algebra of the subsets of real numbers that includes open intervals. And from open intervals, by using countable, union or intersections, those countable number of set operations, you can always construct these sets. For example, last time I skipped that one. For example, suppose you consider some open sets like this, and you intersect, is it intersect? I'm sorry, yeah. You intersect these sets, okay? So this A sub n is an open interval from negative infinity to 1 plus 1 over n. Here n is a natural number. Then by changing this value n, you can have countably infinite number of open sets, right? Open intervals. And then consider countable intersection of these open intervals. What is that? If I remember correctly, it is this one, right? So even you just constructed this Borel sigma algebra from open sets, actually this Borel sigma algebra includes closed or semi-closed sets like that. So no problem, got it? Anyway, I'm not going to dig more about this Borel sigma field because our results says that, okay, since every real random variable can be made to have these two as the sample space and the event space, we just need to focus on the induced probability space. And this induced probability space may admit some interval like that, or union of intervals, blah, blah, blah. And one interesting thing is this. For real random variable, as far as we can compute the probability of this semi-closed interval from negative infinity to some x, then we can compute any probability of the Borel set. That is one of the results. And what is this? This is nothing but the CDF, which was defined in your undergraduate course using this notation. Got it? So this is the story. for real random variable, you just need to focus on the cumulative distribution function. So CDF is the key to understand the real random variable. And now let's go back to our classification. So since this is a probability like this, it's monotone increasing and bounded by 0 and 1. And when a random variable is called a discrete random variable, when the CDF is a piecewise constant function. So by inspecting your CDF, if it looks like that, then it's a discrete random variable. What if it's a continuous function? Then it is a continuous random variable. When do we say a random variable is mixed? It has continuous part, and if we have discontinuity, it's jump discontinuity. So we have something like this. So we may have continuous part and we have jump discontinuities. Then it is called a mixed random variable. Of course, there are other cases, and let me just group them all and say singular. Okay, so mathematically speaking, there could be more singular random variables than any others, but in engineering sense, mostly we just need to focus on continuous, discrete, and mixed random variables. Right? Then what is the probability density function and what is the probability mass function? They are useful in discrete random variables and continuous random variables. And the probability mass function for discrete random variable is very simple. It is denoted by lowercase p subscript the uppercase x for random variable x and the parentheses. This x is a dummy variable. And what is this? It's the induced probability measure evaluated that specific value, the realization or instantiation of x. And interestingly, for discrete random variable, this probability mass function that has probability as a value or 0 is enough to describe or fully characterize the random variable, which means that from this probability mass function, you must be able to compute the CDF. By the way, how can you do that? How can you do that, by the way? So CDF is what? X in the range of the discrete random variable. And what? You have U of P first. Okay. Synchronization issue, there it is. Just a second. P of x at x. Let me say x0, U of x minus x0. So you can easily show that for a discrete random variable, the CDF, which contains all the information about the random variable. In that case, we just say that the CDF fully characterizes the random variable. And the CDF of a discrete random variable can be written this way in terms of the U function. Here, the U function is defined as a right continuous unit step function, which means that its graph looks like this. 1, x. Got it? So countable summation of unit step functions are piecewise constant functions, right? So we have that. For a continuous random variable, probability density function is very useful. However, the probability density function is defined like this, denoted by a lowercase f subscript random variable x of some free variable x, and it's defined as a derivative of the CDF. However, as you see in this discrete random variable case, this continuous function is not differentiable. So what do we do? If we focus on discrete random variables, continuous random variables, and mixed random variables, actually, by introducing the direct delta function, we can describe the PDFs. So, for example, even though mathematically speaking, the PDF of a discrete random variable does not exist, we can say like this. By using the direct delta function. By the way, you learned in signal-gen systems the direct delta function, and I'm not going to review that, okay? As a graduate student, you do it yourself. Anyway, CDF is the most important thing. PMF is useful only for discrete random variables. PDF is useful for continuous random variables with differentiable PDF. However, for almost every practical random variables, by introducing direct delta functions, you can just handle this PDF. And PDF is very, very appealing concept because it is related to the notion of histogram. In statistics, probably you've worked with histograms. First, you tabulate your statistics, and then what do you do? In order to visualize, you divide the kind of range into bins, non-overlapping bins with some width, and then you count the number of realizations or occurrences in each bin. Then you have what? Some kind of bar graph, right? And then what you do is like this. You normalize the height by dividing the height by the total number. In that case, you normalize the kind of vertical scale. So if you add up these numbers, now less than 1, they add up to 1, right? So it seems it's now has become very similar to a probability mass function. We step further. What we do is that because our bin width can vary by choosing different bin sizes, what we do is that the probability, that value corresponding to the previous bar becomes the area of this bar. So you kind of introduce new height equals new height times the width of the bin becomes the probability. And then you can integrate this piecewise linear function of the normalized histogram, then you have 1. So now it becomes more and more closer to what you know as a PDF. Then what is a PDF? PDF could be imagined as a limit of this normalized histogram, right? Here again, you may say that, oh, precisely speaking, how can I consider the limit of a function? But as I told you, what does that mean? For sufficiently large number of bins, for sufficiently small bin width, or by just open your eyes very slightly and see what you have is what? A smooth function that could be integral. And then you suddenly have a PDF. That is the notion of PDF. So I will give you a big important trick. Whenever you have to handle a PDF, just think about, start from the called scatter plot that is equivalent to your table, right? You just, if it is a 1D data, you have a straight line and you put dots first. That is called a scatter plot. And then you introduce bins to construct a histogram. And then make the bin width smaller and smaller, but the height times bin width corresponds to the kind of ratio of the number of occurrences divided by total occurrences. That, in the limit, is the probability density function. By the way, you do that process to understand how you can have from this CDF to that PDF with delta function. Remember that a delta function is a function that integrates to 1. But it has value 0 except that argument 0 point, right? But you may say that, well, is that possible? Again, what you do is that for sufficiently small non-zero interval that has some very big value, but the width is so small so that you can integrate to have 1, something like that. So direct delta function must be understood in that way. As far as our physical resolution allows, we cannot measure the width. However, mathematically speaking, the width may be non-zero, something like that. Got it? Anyway, so after introducing the notion of scatter plot and a histogram, the notion of PDF is very, very natural. So in many undergraduate, or when I was a high school student, we were taught first from the probability density function or mass function, depending on whether the random variable is discrete or continuous. Okay. However, what is the most important thing? The CDF, because CDF is directly related to the induced probability measure. And combined with the real set as the sample space and the Borel sigma algebra as the event space, it becomes a complete induced probability space. Got it? Here goes the preview. I already talked about what is a mixed random variable. There is another special case called a mixture random variable. And let me show you where it is. Yeah, here it is. So this is a rough definition. For a precise one, you find it from the later pages of my handout. Okay, you study that. If you don't understand, just find the corresponding video lecture and study that. Okay, suppose you have a situation like this. You are given 2 random variables, x and y. So you have 2 random variables, and you construct a new random variable z by doing this. Z equals x with probability, I'm sorry, it must be p. Okay, and the random variable z equals y with probability 1 minus p. And then I will ask you, what is z? What is the CDF of z in terms of the CDFs of x and y? What is the PDF of z in terms of the PDFs of x and y? And you can easily show that the CDF of z is the weighted sum of the 2 CDFs. Look at this. I used a dummy variable or free variable z. So on the left-hand side, so on the right-hand side, you must evaluate the CDF of x with z. No problem, right? And CDF of y with z, not x and y, because your variable is now z, right? And then see that here, p is multiplied to the CDF of x, and 1 minus p is multiplied to the CDF of y. In this case, it's a weighted sum, or you can say mixture of two random variables. Since the PDF is simply defined as the derivative of the CDF, and derivative is a linear operator, you can differentiate the first term, you can differentiate the second term. So you have what? The PDF of Z is the weighted sum of two PDFs, or a mixture of these two. By the way, probably from your machine learning course, you heard a lot about the Gaussian mixture. What is a Gaussian mixture? It's a mixture random variable. And what are mixed? Gaussian random variables. Possibly with different, definitely with different means, and possibly with different variances. For example, suppose you have a Gaussian random variable x. Unfortunately, we use n because Gaussian is sometimes referred to as normal, n, mu x, sigma x squared. Of course, some people love to use standard deviation instead of variance, but more people use the variance instead of standard deviation as a parameter. Suppose y is also Gaussian with mean mu y and sigma y squared, and x is chosen with probability p, y is chosen with probability 1 minus p. Then what happens? Let's say this is 1/4, and let's say 3/4, and 0, 1, and 1, 2. Then what happens? Here at 0, you have density of Gaussian, okay, with weight 1/4. And here at 1, you have a density of Gaussian with larger variance. So what would be the overall shape of this mixture random variable? It's something like this, right? So whenever you are given a very smooth PDF, actually you can approximate that PDF using a Gaussian mixture. Of course, sometimes you need many Gaussian random variables. However, it seems it's possible, right? Given any shape of density function, you just approximate that as a weighted sum of different Gaussian densities. So a Gaussian mixture is very useful. Another thing is that, as you've just seen, this Gaussian random variable can be parameterized by only two values. So you just need small number of parameters to describe that, even though number of Gaussian random variables could be large. Okay. So we've seen so far up to the notion of mixture random variable. Now, just a second, where are we? Yeah. So we've just done elementary definitions. Let's move to something more important and complicated. As we remember, in our previous chapter, after we learned the notion of what? The probability of the event over random experiment and related terms, what did we do? Mathematical modeling of that, right? Using probability space. And then what? We defined the notion of what? Conditional probability measure. By using the given probability space and choosing one event that has positive probability of occurrence, right? So we define new probability measure and new probability space and called it a conditional probability space, conditional probability measure, right? And suddenly we had a chain rule that looked very interesting, right? And then, even though not many courses emphasize, I asked you to focus on the fractions, what? The posterior probability of event A divided by prior probability of event A, that always equal to the other ratio. It could be greater than 1, less than 1, or equal to 1. And usually, whenever we have such a case, we focus on the case with equality, because that's very special case. It's a kind of boundary, right? Yeah. And in the boundary, we have some limiting some property. But anyway, so in that case, what do we have? The posterior probability equals the prior probability. What does that mean? Occurrence of the event B does not affect the probability of event B, whether it is occurred or not. From that, the notion of independence comes out. So you have to kind of understand this flow of new notions, right? So before in chapter 1, we had introduced the conditional probability measure, something like this. And then chain rule, and then notion of independence of two events. And then we extended the independence notion to the independence of two groups of events and multiple events, right? And also conditional independence. And then what did we do? We derived two theorems. One is so-called the total probability theorem, by introducing a partition of the sample space. And the most celebrated one, Bayes is the name, so apostrophe must follow Bayes. Bayes theorem. Bayes theorem is a mere combination of the definition of the conditional probability and the total probability theorem. However, it's very, 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 very important. That's what I told you. We do the same thing after we introduce the the random variable. So we are going to talk about conditional probability in terms of a random variable. We will talk about chain rule in terms of a random variable. We talked about independence of something in terms of random variable. We are going to talk about total probability theorem in terms of the random variable. We are going to talk about Bayes theorem in terms of a random variable. Got it? So if you just could not remember some of them, you have to review that part. Got it? Even though I do not cover that all in today's review, because I have to move on to the next chapter very, very quickly. So let me briefly point out what I have punched in the lecture note. So we are where? We must work on here, okay? But it seems that this is not that different. So let me move down to the corresponding part. Here it is. Actually, we are covering a lot, right? Very fast. Oh, okay, here we go. So let's remember the definition. In this case, A and B are interchanged, but it doesn't matter, right? So probability of event A given or conditioned on event B is what? The intersection probability divided by the probability of event B. And now, since we have a random variable x, we want to replace one of the event or both of the events by using the random variable x. That's the idea, okay? What is the most simplest or fundamental event in the Borel set? Of course, the Borel sets are generated by open sets, but as you remember from the definition of CDF, something like this, right, is one of the most important event. And this is also simply denoted by the event capital X less than or equal to lowercase x. So let's just consider this as A event on the left-hand side or B event on the left-hand side. Got it? Or you can just take an event B, a Borel set from the Borel sigma field. Okay, so the notation is a little bit confusing because in this case I used a different type set to denote the Borel set. So this is not Borel set. This is, you just say that this is event B, okay? So let's just take a Borel set from Borel sigma algebra, okay? And then we have to use the event something like this. The random variable x is a member of the Borel set. What does that mean? It's definitely an abuse of notation because we can't say this, right? We always have to talk about something like this. Okay? Set of outcomes x real such that x in B, actually. This is the precise definition. And this goes into the induced probability measure. However, how did we promise to use this one? Simply just use PR x in the set B, right? Got it? So using this probability, what is the probability mass function of x when random variable x is discrete? Okay, so in this case, actually, we both change the set A and set B. Before we consider this one, and here we choose set A as x equals x, set B as x is a member of set some, let me say, B tilde, okay? Yeah, B is not B, okay? So after we replace A and B, we simply have the new conditional PMF in this form, right? It's not that difficult. We can also consider conditional CDF, right? By differentiating this one, we can define conditional PDF. Very simple. Okay, so let me be more specific because you already got confusion. So given a random variable, so given this induced probability space or the CDF directly, okay. First, x is discrete. And you choose some set B, something like this, okay? Then I ask you, what is the conditional probability mass function of x given event B? And I will denote in this way, okay? So in the subscript, I will put the conditioning bar and B. Of course, you may say that this is not a good notation. Probability mass function of x given or conditioned on event B may be better. You are right. So some people love this notation. Some people use this notation. And it's your preference. Anyway, what would be this one? So we go back to our definition. What is this? The conditional probability of event that random variable x has instantiation or realization x, given the event x is a member of the set B. In this case, B could be that one. And then we just use since now we have general probability, right? Or you may say the PR if you want, then probability of event x in B and probability of event x equals x intersection x in B, right? And then you compute the individual events probability, and then that becomes the conditional probability mass function. Okay. Let me be more concrete. So suppose you have a fair die, and I will ask you something like this. So what is the probability mass function of random variable x, given x is an even number? When you toss a fair die, what is it? Can you visualize that? Can you draw a graph of this probability mass function? And you, of course, know that 1, 2, 3, 4, 5, 6, and the result is something like this. Okay, you can easily apply the definition and find this. So the principle is this one. Apparently, it seems complicated to derive the conditional probability mass function. However, if you go back to chapter 1 and just resort to the definition of conditional measure, you are done. No confusion. Okay? And conditional CDF, since that is also probability, conditional probability, as you see here, right? Consider the conditional CDF of x given the event B, then what? What is this one? It is simply probability of event that x is less than or equal to x given the event x in B. So you have the exact case of what we learned in chapter 1, conditional probability. And then you use the definition and modify it to it with the in terms of unconditional probabilities cumulative distribution function. So that's all. So here I've written like this. This definition, conditional CDF, applies to discrete, continuous, and mixed random variables. You can do anything. Conditional PDF, simply derivative your conditional PDF in principle. However, you can just derive it by inspection. Okay? For example, in this case, what is the conditional PDF of x given x is even? Then, by introducing the direct delta function, usually we use double arrow, something like that. Okay? And you do everything. By the way, if you read my handout, whenever I define something, or usually after defining some notion, I check existence and uniqueness. And this should be your habit too. Okay? Whenever you want to argue with some other people about something, try to introduce the definitions of terminologies you are going to use in the argument. And then carefully examine whether each new term satisfies this existence and uniqueness criteria. If that new concept is not guaranteed to exist, then all the following argument has very small meaning or no meaning at all. That is often forgotten by religious people. For example, you are a Christian. You want to persuade your boyfriend or girlfriend to become a Christian, and you try to persuade him or her. However, if your friend does not accept that the God exists, then no argument possible. Okay? So that's the most important part, existence. And what would be the next step? You must check whether that concept is singular or plural or not. Okay? That is often becomes the problem to Koreans and Japanese and Chinese, because these Northeastern Asian people have developed their language without article. In Korean, 관사, 정관사, 부정관사, or on such a thing. Interestingly, Western Europeans, I believe their language made them more mathematical and scientific, because as you probably learned in German or French language, the plurality is very important when you talk about something. So whenever they discuss about something, they just automatically think about whether it is unique or not. Okay? There could be many, many of these or not. So they are very precise. And so that's why many scientific, even mathematical book does not talk much about the existence and uniqueness, because it's just natural. After define something, they just think about uniqueness and existence. And then they reflect that notion, that discussion in their use of articles. By using they just imply that it's unique. Okay? So after you define something, if the article the follows everywhere, then that is unique just. Okay? However, if they say or something and put S, like boys, girls, what does that mean? It's not unique. So it's natural. However, the Koreans, we have big problem. Okay? So to become a better scientist or engineer, you have to make it a habit. Check the existence and check the uniqueness. The difference between existence and uniqueness is that if existence is not guaranteed, then your argument following has very low meaning. However, existence just makes you think more clear. Okay? It's not like everything must be unique. Okay? However, you have to focus on whether it's unique or not. That's very, very important, because in engineering problems, in many engineering problems, you are just happy to find an optimal solution. There could be many optimal solutions. However, in many cases, you are satisfied with an optimal solution. The problem is that in many theses, it's much better to find all optimal solutions if we have more than one. Do you understand what I mean? That is termed as the solutions are fully characterized in this paper or something. So given some problem, you find all the optimal solutions. That is a great thesis. If you find just one solution, may be good, because suppose no one has found any optimal solution yet, then the first finding could be very important. However, if somebody found most of the practical solutions already and you find some impractical solution, then its value would be very, very small. So this thinking about the uniqueness and non-uniqueness is very, very important anyway. So that is related to this existence and uniqueness parentheses. Oh, here goes a very interesting problem. So I will hide that from you, and let me write it here. So suppose you have a Gaussian random variable x with a mean 0 and variance 1, which means that its density function is simply the bell curve centered at the origin. Okay, so you have something like this. Here goes the question. What is the probability density function of x conditioned on x squared equals 1? Okay. Find the conditional density. Actually, I really loved this one. So when we had the graduate entrance exam, and I sometimes put this question. And as I expected, more than 2/3 of the applicants got incorrect answer. So this is a very notorious problem. So what is that? Given a Gaussian random variable, what is the conditional PDF of the Gaussian random variable conditioned on the occurrence of x squared equals 1? What would be that? Your intuition says what? Given x squared equals 1, what does that mean? X is either 1 or -1. What is the density of x? And you can only have 1 or -1. And from here, 1, x equals 1, and x equals -1 has the same density value. So your intuition says that this must be 1/2 delta of x minus 1 plus 1/2 delta of x plus 1. And you are right. But how can you show that is correct? That's another problem, right? So what do? Whenever you have problem to precisely derive your answer, consider this conditional CDF that differentiates to become this conditional PDF. What is that? Probability of event that x is less than or equal to 1 given x squared equals 1, right? Now, this is what? This is simply the conditional probability of event given another event. So you can just enjoy your previous techniques handling this conditional probability. And in case you need, you can rely on total probability theorem or Bayes theorem if you want. And try to derive this one. And you can show that that is what? That looks like all 0 up to -1. And you have a jump, sorry. You have a jump discontinuity to 1, and you have another jump. And this is 1 and 1/2. So this is the conditional PDF of this Gaussian distribution conditioned on x squared equals 1. So what? You differentiate this one to have that one. Got it? This is the idea. So try to do this exercise. Got it? What else do we have? Let me see. Oh, chain rules. Chain rules. What are the chain rules? We have some situation like this, and we have two different equalities. One with unconditional probability of event A, and the other, the conditional probability of A, right? And now you have a random variable x. So what you do is that you either change this event in terms of x, or change this event in terms of x, or both. So you can think about such joint probability of event. And here comes what? If you rely on that equality, you first have the probability of event B and the probability of event A, which is the semi-open interval, semi-closed interval, you may say, given B. So you have suddenly conditional CDF, right? And what about this one? This is most challenging part. Okay. Probably in the previous problem like this, once you have written the conditional probability of event x less than or equal to x given x squared equals 1, you have focused on this one. And you have said that this is 0, right? In Gaussian, probability of event that you observe x squared equals 1 is 0, right? Because it's a continuous random variable. So this is called so-called, this kind of thing is called point condition. Okay. Before, I told you, in order not to divide by 0, right? We must have some event with non-zero probability when we talk about conditional probability. Am I right? However, definitely after we introduce this notion of random variable, especially when we consider continuous random variable like Gaussian, this point conditioning has some problem because probability of this point event is 0. We cannot divide by 0. What do we do? So in such a case, as I once told you today's lecture, think about small interval, very small, but not 0. Okay? This really appeals to our physical or engineering application because anyway, this world is not continuous. That's what modern physics has discovered. In Newton's world, after Descartes introduced the coordinates, people more and more think about or understood this world as what? A kind of continuum. And that actually prevails in kids' cartoon. For example, in the Magic School Bus, what do? They shrink their bus and go into a body. And what happens? Even though it's shrunk, they just live a normal life. Does that make any sense? What about life's molecule? Is it shrink? Is it shrinked? Right? So that doesn't make any sense. So anyway, as an engineer or scientist, we mathematically model the real world. We are not mathematicians. So even though, precisely speaking, since this event has 0 probability, we can't handle it, but just simply consider this as what? X squared is approximately equal to 1. Then suddenly, from the density function, you may say that, okay, around -1, we may have some interval that could be understood as approximately equal to 1 when it is squared, right? And then no problem at all. So do this, got it? And then no problem, just proceed. For discrete, for continuous, for mixed, you can handle any case later on, okay? So this talking about, consider the conditional scatter plot if you talk about conditional PDF, CDF, PMF, and consider conditional histogram, right? Given conditioned on something. What does that mean? You have a guard that performs in Korean modern term, 입구 cut. So some outcome comes in, then your guard says, okay, you're out. And then you draw scatter plot and you draw histogram. That is conditional histogram or conditional scatter plot. And then you just proceed as follows. Then you can handle anything. That's the key. So here goes some example. So suppose this line, this upper line, upper curve is the CDF of random variable x. And now you have conditioning event that is x less than or equal to some number b. Now, given b occurred, given the event x less than or equal to b occurred, what is the new CDF? And this, okay, I got confused. This lower curve is the original CDF. And after your conditioning with this condition, then you have suddenly what? That curve. It flattens from B to the unity, something like that. And Here we have conditional density. Corresponding to this conditional PDF. Okay, so try to do as many exercises as possible, okay, with many cases. For total probability, almost the same. So it's like you can find the CDF by using conditional CDFs with some partition of the entire sample space. Okay. You can do the same thing to derive the PDF. Actually, these kinds of conversion of the unconditional CDF or PDF into the weighted sum of conditional PDFs and CDFs. You see that the right-hand side is what? CDF, conditional CDF times some probability, summed. This is a weighted sum of conditional CDFs. This is what? Weighted sum of conditional PDFs. These tricks are very important in any statistical inference, estimation, detection, in AI terms, classification and regression. So you must pay much attention to this formula. You can also do a similar thing. And here goes something very interesting. Once I told you an indicator function is what? It's a function that maps any input to 0 or 1. If the input is a member of this set in the subscript, then your output is 1. If not, your output is 0. So it indicates whether it satisfies some condition, right? Now, let me say that this indicator function is very important in converting the unconditional things to conditional things. For example, let me go back to some previous page. Where it is? I remember. Yeah, here. So suppose you want to rewrite this conditional probability mass function of random variable x, so x is discrete, in terms of the unconditional probability mass function of x. So this is what? This is px of x. Okay? And what is this one? This is sigma of pxx, unconditional PMF, for all x in the set B, right? So this conditional mass function can be written as, according to this claim, indicator function subscript b of x times px of x divided by sigma x in b px x, okay? Of course, it's confusing, so you may say x tilde here, okay? So x is variable, right? And then on the right-hand side, you have an indicator function times this ratio. What does that mean? This is the guard that performs equal cut. Got it? And you can easily show that the left-hand side equals the right-hand side. So indicator function is very useful, even though most of the undergraduate books does not use. They just vaguely explain. However, if you take a look at a more advanced book published by mathematicians, they really love to use this indicator function. And that's also the case with this course. So I'm going to intensively use this indicator function. Got it? So I hope you got acquainted with it soon. Get acquainted with it soon. So here goes the example. So you want to, given the random variable, continuous random variable x, you want to compute the probability of x, instantiation of x is a member of the event A. And then you can show by using the total probability theorem, then suddenly it becomes integration of your density function over the entire real line times indicator function. By the way, without this, which means that this is all 1, what do you have? Density integrates to 1, right? Because it's probability. Now, what does that mean? Only the case when X is a member of A, your density survives, so it contributes to this probability. It's natural, right? So use of indicator function is very, very powerful. Same thing can be done for other cases like this, Bayes' theorem. Now, suppose you want to find the conditional probability mass function. Oh, this is already done, right? So you want to find a conditional CDF of random variable X given some event, given as a Borel set, then the lower case is definitely, even though I use the Stilchus integral, probably you are not familiar with it, you can just interpret it as what? As something like this. Indicator AX, density of X dx, and integration indicator X tilde, density of X tilde, dx tilde, something like this. Okay. We don't need that. It's fine. Okay. Yeah, something like this. Yeah. So this X goes here. Okay. For other x's, tilde, X primes are not X. Okay. So again, indicator function is very useful. Now, about independence. Before we had this formula for 2 independent events. Now we have a random variable. So again, wants to replace one of the events or both in terms of the random variable. Got it? So here goes the first question. You have a fair die, 1, 2, 6 as outcome. And you have, okay, you roll twice independently. So it's a very simple sequential experiment. It is a combined experiment with, usually we assume, with independent combining to get the combined probability measure, right? You just multiply simply. Now, X is the sum of 2 realizations, okay? And what is B? Event B is the sum of 2 is 7, okay? So let me just say that yeah. So X is the random variable representing the number shown in the first Rowling. Okay, so you have X and you have Y and Z equals X plus Y. So precisely speaking, this probability is that X equals 3 given Z equals 7. Okay. And the question is this conditional probability same as unconditional probability? So probability of X equals 3. And you can show that they are independent. Okay. And in this case, we have random variables, right? So independence can be applied to random variables. And now we introduce new definition. One is this. Random variable is independent of an event. What does that mean? As I emphasized again and again in the last 3 meetings, we had what? We had the definition of independence of 2 events, right? 2 events. Now we want to extend it to an independence of 1 event and 1 random variable. What do? Of course, we construct any event in terms of this random variable X. And this event, if this event in terms of X is independent of that event, we want to say the event is independent of the random variable. Got it? So it's different. There could be many events generated using X. Got it? But in terms of our CDF, people have shown that this is enough. to talk about independence of a random variable from an event, you just need to show that this event, this joint event of x less than or equal to realization x intersection B is the product of the CDF and the events. Okay. What does that mean? This is as far as probability of event B is positive. This is same as this one. Conditional CDF of x given B equals unconditional CDF of x for all x real. Okay. Now it's over time, but it's very important. We are almost there. No. I will just stop here. So this is the idea of our extension. Any event, but it could be restricted to semi-closed interval from negative infinity to some x. That event for all x is independent of the event B, then the event and the random variable are independent. Got it? So we are done with the second chapter. Unfortunately, even though I updated third chapter, I couldn't use it. But next time, we are going to talk about expectations, one of the most exciting topic in probability theory. And there are much about to talk because it's an interesting topic. Anyway, I hope you enjoy the second homework. It will be a lot again, and you are allowed to discuss, okay? Of course, I will try to give you the problems from my previous quiz, homework, and exam, especially most of them with solutions, so that you can quickly study. The purpose is to quickly review the material, okay? So in the open chatting room, try to discuss a lot, even share your solutions. As far as you write your own solution and submit, your full discussion, cooperation among you, and even with your father in law school or even your mother in English department can help you, okay? No problem in this case. Okay, that's all for the day. Have a nice weekend with many homework problems.